so to start things off today, I want to wrap up this unit, and essentially we just need to talk about minor losses. So just to kind of recap where we were at last time. So we talked about the head loss equation, which, yeah, this is the version I want to talk about. So we have these first two terms on the left-hand side look very similar to the Bernoulli equation with some corrections for whether the flow is turbulent or not. And then we also have a bunch of added terms that kind of take into account a more realistic system. So we can have work coming in or out of our system. And then we also have losses in our system. So we break our losses down into major losses and minor losses. If you recall, when we talked about major losses are just the losses basically due to friction in long sections of pipe. And then the minor losses are going to be losses that come as the fluid passes through things like fittings. Okay, so for the major losses, essentially the process is you first calculate your Reynolds number, and then you calculate your friction factor. This is going to depend on, I'm sorry, not your friction factor, your relative roughness. Your relative roughness depends on the material of your piping. And then you use those two pieces of information to find the friction factor on the Moody diagram. The Moody diagram is what you're going to be using in exams because you can't just numerically find the solution to this equation on the exam. But if you need something more accurate, in practice, once you go and get a job, you can certainly use that equation to get a more accurate answer than just reading the chart. Okay. Yeah.
The diagram, that was for the minor losses or the major, or just for both?
This is for major losses.
Oh.
So this is to find your friction factor F. All right, and your major losses are always going to have this form. Where's my highlighter? Right, so this is going to be the expression that you'll use to figure out your major losses. And then that friction factor, you just use 64 over the Reynolds number if it's laminar. If it's not laminar, then you gotta do the chart. Yep, that was a good question. Other questions before we go on to the minor losses? All right. Okay, so minor losses, like I just mentioned, those are losses that are going to come from going through fittings or kind of abrupt changes in direction, that sort of thing. And so you can calculate them in two different ways, actually. So these can be calculated. In two different ways. The first way is to use an equivalent length. So our minor losses will use this equivalent length, the average velocity over 2D times F. All right, and this is very similar to the Darcy-Weisbach equation from our major losses. And this LE here, that is your equivalent length. And what the equivalent length means is that for any minor loss, so the losses affiliated with going through a fitting, for example, the equivalent length is the amount of straight piping you would need to have the same amount of loss as going through that fitting. So this is the length of straight pipe to yield the same loss as the fitting. Yep. So the little e is equivalent. And then L is length. All right, so that's why this looks like the Darcy-Weisbach equation, because it kind of is, but you're using this effective length to take into account the loss through the fitting. So you're saying if the fitting wasn't there, my losses would be the same if I had a straight section of tubing that had a length LE. Okay. The second way that we can do this is the following. We have our minor losses is equal to our average velocity over 2 times K, where K is called the loss coefficient. And all K is essentially the grouping of these terms together. All right, so we can package up LE times F divided by D and just call that a loss coefficient K. So I'll just write this more explicitly. So LE times F over D is what K is. All right, and just as a small note, LE and then thereby K depend on geometry. So what type of fitting you have, Reynolds number, all that good stuff. We use lookup tables to find these. So if you're following along in the book, this would be tables 8.2 through 4, and then figure, so these are tables, and then figure 8.15. Another little picture I want to draw to kind of explain the effective length. So if you have a T fitting that looks like this, and this has some length L, the pressure drop through this fitting is equivalent to the pressure drop for a straight tube of length LE, and it will always be the case that LE is greater than L. So you'll need more straight length losses to equate what comes from the losses in the fitting. Yeah.
We weren't really taught that well how to use lookup tables.
I'm gonna walk you right through these. Yep. And these ones are pretty gentle, especially if you're talking about like thermodynamic tables. There's no interpolation required for these. I would have been happy to walk you through it anyways, but there's not interpolation, so you should find these tables to be a little nicer or at least more straightforward to deal with. In fact, I'm going to show the tables to you now. Okay, so these are the types of tables that we are going to be using. So if you want to use the equivalent length, formulation for minor losses, you might use a table like this. So just keep in mind that this is LE divided by D, not just LE, right? And then on the leftmost column, you'll have different types of fittings. All right, so you've got different types of valves. All of those are considered to be fully open. Standard elbows at 90 and 45 degrees, return bends, all that good stuff. We also have tables and figures that will help us find our loss coefficient K. All right, so these next two tables are going to show us K, so we're going to have to use that version of the equation. All right, so outside of fittings, we also have losses when we have fluid entering into a system in different kind of geometric ways. So this middle table shows us those different types of ways. This first one, just so it's abundantly clear, this is like if you were to have a tank and then you have your pipe extending into it like this. So that's this one. Trying to make that clear. But essentially you have like a fluid in a big reservoir, and then it's going into this piping system like this. Does that make sense? More or less? Okay, cool. And then this second one is the same idea. So you have some very large kind of body of a fluid. Oops. And then it's entering into this pipe flush. Okay. This is two. And then, you know, of course, the third one there is the same idea, but just rounded edges. Okay. For the rounded edge one, you'll notice that you're going to need to know information about how that edge is chamfered. So the ratio of that turning radius over the diameter of the pipe. You'll use to find K. And then this one, come on, this is the toughest one to use, this bottom one. It's not quite interpolation, but I think initially this chart is a little confusing. So I'm going to show you a color coding on it that will hopefully clear it up. But essentially, if you have a pipe that kind of very quickly contracts or expands, there will be a loss affiliated with that. So the first step that you want to do is identify whether you have contraction or expansion. All right, if you have contraction, so if you're going from a bigger pipe to a smaller pipe, then you want to calculate your area ratio using the smaller one divided by the bigger one. Okay, so that's this step here. This figure kind of guides you through the process. All right, if you have an expansion, then you're going to look at this one, and your area ratio is going to be A1 over A2, which again is the small one over the big one. All right, so whether you have expansion or contraction, you're gonna always put your smaller area of your piping on the numerator and then the bigger one on the denominator. The next thing that you're gonna do is you're gonna take that area ratio that you calculated and find it on the horizontal axis. All right, so you're gonna have a look at where it lives on this spectrum here. And then the third thing you're gonna do is you're going to find where that area ratio intersects with the curve that you want. So there's two curves on here. One is for expansion and the other one is for contraction. Okay, you'll notice that they're both the same color, but they have arrows pointing to the left and the right. Our left-hand axis is the contraction one. So this curve is contraction. And then the expansion curve points to the right-hand side vertical axis. So this one is contraction. Okay, so for example, if you had an area ratio of, let's say, 0.4. So this is 0.4. I'm gonna draw this up. Here's my intersection point for if I have a contraction. Here's my intersection point if I have an expansion. And I'm gonna draw this line over to here. So if I have an area ratio of 0.4, the K value for contraction is about 0.25 for contraction. And my K value for expansion is roughly 0.4. Does that make sense?
So how do you know which one's contraction?
Oh, that's okay. So it says on the vertical axis which one is which. So this one is contraction and this one's expansion. Do you mean like in your system, how do you know which one is which?
Yeah.
Okay, so I would refer to these pictures up front or up top. So if your pipe is going from a large diameter down to a small diameter, it's contracting, so it's getting smaller. If it's going from small to big, then it's expanding. Yep. Okay. Okay, so now that we've seen the head loss equation and we've talked about how to deal with if there's work added into the system or taken out of the system, and then how we account for major and minor losses. Let's do an example now and put it all together. Okay. Okay, so in this example, we have a system that's using water at 60 degrees Fahrenheit, and it's flowing from the basement in a house to the second floor. So essentially, this is a household plumbing problem. And we are told that we have 3/4 inch diameter copper pipe. And that copper pipe is a drawn tube type, so we're gonna use that for our relative roughness. And we have our flow right here, so we have 12 gallons per minute. And it's exiting through a faucet on that second floor that has a diameter of 1/2 inch. We wanna find the pressure at the inlet to this system, so at 0.1, using three different kind of approaches. So the first one is we're gonna neglect all losses in the system. The second one is we're just going to include major losses. And then for the third one, we're gonna include all the losses, so major and minor losses. Okay? Does the setup make sense? Yeah? Okay, cool. So let's start with writing down our governing equations. We have our head loss equation. So we have P1 over rho G plus alpha 1 V1 squared over 2G plus Z1 minus P2 over rho G plus alpha 2 V2 squared over 2 plus Z2 plus H pump in minus H turbo machinery out. And this is equal to our major losses and our minor losses. Okay,
But with the G underneath, so I know it's usually Z times G.
Yep.
Do we have to divide it?
You don't have to. No.
You can do it.
Yep, you can do it either way you want. That's fine. Okay, so when we approach these problems, one of the first things that I would suggest that you do is figure out where you want to put Z equals 0. All right, so we have, this is our 0.1 and this is our 0.2. Does anybody have any suggestions for where we should put Z equals 0? At 0.1, okay, great, yes. So just to remind you from when we did the Bernoulli unit, it does not matter where you put Z equals 0 as long as you're consistent with measuring the Z values for 0.1 and 0.2, noting that if you go down, it's negative, okay? Okay, so if Z is right there, that means that we have Z1 is equal to 0. Can anybody tell me what Z2 is based on this picture? Yeah, 20 feet. Fantastic. We want to find the pressure at 0.1, so I'm gonna just put a little find this. Right here. Do we know anything about the pressure at 0.2? So anytime we have a fluid discharging to the atmosphere, we can assume that it is at atmospheric pressure at that discharge point, okay? So this is P atmosphere. All right, what about our H pump and our H turbo machinery? Do we have any work input or extracted from this system? Yes, so there's nothing here. And there's no turbo machinery adding work to it either, right? So I can get rid of both of these. Yeah. Yeah. So these, I will just bring you back to here. Maybe. Okay, so if we divide by mg, this is sometimes called H pump. And this is H turbo. So these are the W dot terms from work either put in or extracted out from the fluid. Okay? Does that make sense?
Yeah, but how did you know?
Oh, how did I know that there was nothing? Okay, so if we go back to this picture, a turbo machinery is going to look like a turbine in the system or a pump in the system. And if it's in here, it'll be clearly called out by the picture, but we can see that as we go from point 1 to point 2, we're flowing through straight sections of pipe, some threaded elbows, a valve, and a faucet. That's it. There's no pumps in here, no turbines in here, extracting energy, none of that, okay? It will also, well, it'll say something about it generally. Either it will ask you to find how much work you need to put into the pump to achieve a pressure, for example, or it will tell you how much work it's putting in to the system. Okay. All right, cool. Okay, great. So we've kind of taken all of the things that were easy to find out of this problem. The next thing that we want to sort out is these terms here with the velocities. All right, so we need to figure out the velocities at point 1 and 2, and then we also need to figure out what alpha 1 and alpha 2 should be. So we decide the value of alpha 1 and 2, whether it's laminar or turbulent. So laminar, it gets a value of 2, turbulent, it gets a value of 1, which means we need to find the velocity, and then we also need to find the Reynolds number. Both of those at point 1 and 2, okay? So our next step is find V1 and V2 and Reynolds number 1 and Reynolds number 2. Okay? Okay, so we were given flow rate. So we are given Q is equal to 0.0267 cubic feet per second. And we're also given that the diameter at 1 is 0.0625 feet. And that diameter 2 is 0.5 divided by 12 feet. All right, so I am going to make use of the fact that Q is equal to V1A1, which is equal to V2A2. So it's just the definition of volume flow rate, right? All right, so this means that V1 is equal to Q divided by A1, and V2 is equal to Q divided by A2. Okay. All right, so let's do that. I'm gonna just kind of move my work over here. So V1 is equal to Q divided by A1, which is 0.0267 cubic feet per second, divided by area 1, which is pi, divided by 4, D1 squared, which is 0.0625 squared, and this is square feet, which gives us 8.7 feet per second. So here is V1. So we've got that. And then we're going to do this exact same thing for V2. So this is Q divided by A2. So we have 0.0267 cubic feet per second divided by pi over 4, 0.5 divided by 12 squared, feet squared. And that is 19.6 feet per second. All right, so we have that. That's good. All right, so now we need to calculate our Reynolds numbers. So our Reynolds number at point 1 is V1 times D1 rho over mu. Or mu over rho is nu, is the kinematic viscosity, right? So I can also write this as this. So we've got 8.7 feet per second times 0.0625 feet divided by the viscosity. So this is something we would look up, or it would be provided to you on an exam. This is 2.34 times 10 to the minus 5 square feet per second. And this equates to 45,000. So what do we think about turbulent versus laminar? Turbulent. So this is greater than 2,300. So this is turbulent, which means that we are going to select alpha 1 equals 1. So this is equal to 1. Yeah.
It always turns into kinematic viscosity.
I'm sorry, say that again.
Does it always turn into kinematic?
Yes. So nu. So by definition, nu is equal to mu divided by rho. So anytime you have this, you get this.
Oh,
That's always the case. Okay. Okay, so let's find Reynolds number at point 2. So we have V2 D2 rho over mu. And again, I'm going to make this V2 times D2 over nu, which is 19.6 feet per second times 0.5 over 12 feet. And then viscosity stays the same as last time. So we have 2.34 times 10 to the minus 5 feet squared per second. And this is 34,900. Which is again greater than 2,300. So this is also turbulent. So we're going to say that alpha 2 is also equal to 1. So I have alpha 2 equals 1. Okay, so we have everything on the left-hand side of our equation taken care of, which means we can do part A. So if we neglect all of the losses in our system, we're assuming that HL and HLM are 0. And we can find P1 that way. So I am going to solve this main equation for P1. So I have P1 is equal to rho GZ2 plus 1/2 rho V2 squared minus V1 squared. I've taken into account that alpha 1 and 2 are both equal to 1. And then, actually, let me move this down. This, we also add in rho times capital HL plus rho capital HLM. All right, so once we put gravity back into the losses, they become the capital H. All right, so this is our equation that we are going to be working with for parts A, B, and C of this problem. All right, so let's do part A. So for part A, we assume no losses. So that means that HL and HLM are both 0. All right, so that means that we just have P1 is equal to rho G Z2 plus 1/2 rho times the quantity of V2 squared minus V1 squared. And that's it, right? And we already have all of this information. So we can just calculate it. So when I plug in all the information that we already have, I get 1547 pounds of force per square foot, which is 10.7 PSI. Oh, yes,
On that example, do you want it English or?
I will always give you metric. I despise working with English units. It is good to know how to do this though, so. It's also nice because if I give you metric on the exam, I don't have to give you a big table of like conversions that are weird and not, you know, like 1,000. The metric system is just better, in my opinion. Okay,
I have a question.
Yeah.
Doesn't matter if it's lowercase or uppercase, I'm gonna keep getting.
yes, so it does matter. So reminder, HL is HL divided by G. So if you have your G's with your Z's, then it's gonna be a capital H. If you have them not with the Z's, then it'll be a lowercase h. So if G's show up in the denominators, you'll have a lowercase h. If they don't, uppercase H. Okay? Questions so far? Other questions? Yeah.
When would we use the lowercase h?
So the lowercase h will be if you have this top form of the equation. So you'll notice that we have, oh, and I forgot this G. We have G's in the denominators. So if you've divided through the whole equation by G, then the H's will be lowercase. The reason that, well, at least my belief for the reason why that this equation gets kind of formulated in that way is because in that sense, the losses are just in units of like meters or inches. So you can think of a system, like a really simple system where you have tubing that curves upwards and it's attached to a pressure or a pump on the one end. The amount of distance that that column rises up the other side is going to go down as you increase the losses in your system. Does that make sense? So I think, you know, that is kind of the intention for why some folks formulate it this way.
So was it something to do with the?
Yeah, so that happened when we solved for, we wanted to, oops. we want to stop that. Okay, so we wanted to solve for P1, right? So if you look in this equation to solve for P1, I have to multiply through by rho times G. So as soon as I multiply the little h times G, I get the capital G because of this. Or the capital H, I'm sorry.
And that's how all the other ones.
Yep.
Okay.
It probably would have been a little cleaner if I just started this equation with the form that had the capital H's, but I just wanted you to see kind of the distinction. Yeah.
So how would you know you need to divide by?
So okay, there's never like needing to divide by G. Like that's never a requirement. It's just, this is a version or a like representation of the exact same equation. And honestly, if you go back to kind of how we set up the major and minor losses, we're talking about capital H's in here, right? So if you have a lowercase h, all of this would need to be divided by G as well. Yeah. My intention with showing it to you in this way is just so that you can be aware that if it's a lowercase h, you have to contend with the G's. Okay, but it's equivalent. Okay, other questions? These are good questions. Okay, if not, let's talk about if we consider just the major losses. All right, so if you remember, major losses are just losses in the straight sections of piping. So here we're going to have P1 is equal to rho GZ2 plus 1/2 rho V squared 2 over V1 squared plus HL times rho. All right. Okay, so these major losses are just straight section of pipe losses. So let's go back to our picture and have a look at the straight sections of pipe. Now, the nice thing is all of the sections of pipe in this system are all the same diameter and they're all the same type. All right, so we basically just need to look at this and sum up the total amount of length of pipe that exists. It doesn't matter that they're divided up with fittings all over the place. For the major losses, we just add up all of the sections of straight pipe. All right, so if we do that, how many feet of straight sections of pipe do we have?
60.
You were on top of it. I don't know who's that. Was that you, Owen? Okay. He understood the assignment. Okay, so for HL, I'm going to write down our equation. So we have L over D, V squared over 2 times F, as Owen already rapidly calculated. L is 60 feet of straight tubing. All right, and the velocity that we're going to use, if you remember, we had a V1 and a V2, right? V1 was for our 3/4 inch pipe, and V2 was when it gets reduced down in this faucet. So we actually have V1 throughout this entire section of straight tubing because it's all the same diameter, right? So we will use V1, which is 8.7 feet per second. We already calculated that. Diameter, it's all the same diameter. So this is D1, which is 0.0625 feet. And then we just need to figure out F. So we're going to use our Moody chart for this. All right. We already calculated before what the Reynolds number was. It was 45,000. So we have Reynolds number is 45,000, which is 4.5 times 10 to the fourth. Right? And then we need to figure out epsilon over D is the other thing that we need from our to read our Moody chart, right? We need to know the relative roughness. So if you remember, I made mention of the fact that this copper pipe drawn tube was going to be important to us. So we're going to use this to look up the relative roughness. All right, so I'm going to take us back to our relative roughness table. Uh, hang on. I thought. So I think. I don't see the drawn copper on here. There are many tables that are similar to this. So I'm going to, I'll just make a note that I got this from a table that's not in the notes. So this is, oop, that's a highlighter. This is 0.0025 millimeters. And then our diameter is 0.0625 feet. Be very cautious about these units, okay? So you're gonna have to convert one of these into the other in order to do this division. All right, and when you do that, you end up with 8 times 10 to the minus 5. And then let me make a note. So this was a table from the book, I believe. On the exam, it will be very clear like what entry in the table you should use. Okay, fantastic. So I'm gonna just copy the Moody chart so that we can put it right where we want it. Okay. So we have our relative roughness is 8 times 10 to the minus 5, which is going to live somewhere in the middle of here, these two curves. All right, I like this problem because it has a relative roughness that's in between two curves. When this happens, you can just kind of eyeball what this curve would do. It's going to stay in between these two bounding curves, so it's going to generally look like this, okay? And then they all kind of collapse over here, so it's going to generally be like that. Okay, so that's our relative roughness curve. Yeah.
Where was the 8 times 10?
Wait, say again, sorry.
Where was the 8 times 10 to the minus 5?
This one. So I took here's 5 times 10 to the minus fifth. That's a little bit smaller. So I know that it's partway between the 5 times 10 to the minus fifth and 10 to the minus 4, because 10 to the minus 4 is 10 times 10 to the minus fifth. So it's gonna be in between 5 and 10. That makes sense? Okay, so this is our curve that we're gonna care about for the relative roughness. Our Reynolds number is 4.5 times 10 to the fourth. So I'm gonna find that down here. So I've got 10 to the fourth, and then I wanna go this is 1 times 10 to the fourth, 2 times 10 to the fourth, 3, 4 times 10 to the fourth. So I'm gonna go halfway between the 4 and the 5 times 10 to the fourth. And I'm gonna follow this up here. All right, so this is our intersection point with our relative roughness curve. And then I'm going to draw this over to the left. And this is our friction factor. So our friction factor is approximately 0.022. Are there questions on how I did kind of any of these calculations or reading of the chart? I wonder if I can clean this up a little bit. No. Okay, so now we have our friction factor and we can calculate this HL. So we have 60 feet divided by 0.0625 feet times our velocity at 1, so 8.7 feet per second. That whole quantity squared divided by 2 times our friction factor of 0.022. All right, so I'm going to take this result and pop it in here. And when I do that, I get that P1 is equal to 20.3 PSI.
So the question in
Yeah.
terms of, the major equation of the HL equation.
Yep.
Does it matter if we use V2 or V2? Or V1?
Yes. It does. So you are going to, and this is a good question because it leads into something I was going to remind you guys of. So we are looking at the losses in this straight section of pipe. So all of these sections of pipe have the same diameter, right? They all have the same velocity. You're going to want to make sure that you're using the velocity and the diameter of the pipe where you're calculating the losses from. Otherwise, it'll give you losses for something unrelated. Okay. That being said, since this problem, all of the sections of straight piping were all the same, this equation was fairly simple. If you have a situation in which some of the pipes are one size and then some of the pipes are another size, you'll have to do this twice. You can kind of group it by, if the pipes have the same diameter and velocity, you can bundle them all together, like how we connected all our pipes and said it was 60 feet. So you can always do that, but if you have differing diameters and velocities, you have to separate them. Does that make sense?
So it's because about the V1 and V1, because it was going in, like one that's going.
So it is not V2 because V2 is happening right at this faucet outlet. So the faucet outlet is narrower than the rest of the tubing in the whole system.
So
Everything else is V1 up until you get to the very end of the system. Yep. Question?
You did have two different like diameters or one Did you just add the major losses or?
Yes, they just sum together. Yep. Great question. Thank you.
Under the exam, we have multiple or at
It-
least two.
It could happen. It could happen.
It won't be like 7.
No, so I will be conscious of like how much busy work I'm giving you, if that makes sense. Because honestly, like, I don't know about you guys, these problems to me don't feel extraordinarily difficult from a conceptual standpoint. It's more kind of like computational busy work. So I'm not going to give you like just a lot of calculated work. I don't, that is not the spirit of what I'm trying to assess. So I think in the past, I've done like 2 different pipe diameters in a problem, just to make sure you know, like, I can sum these together and I have to treat them differently. That would be the assessment. Yeah.
On D1, like it makes sense, I'm just.
On which part?
I don't know how, like, if you gave me this on an exam, I don't think I would know how to tell if it was D1.
Oh, okay. So the way that you know to use D1 is this statement here. So it's flowing through a pipe of this size through this type of tube at this flow rate. Okay, so we know that from, if I just highlight, hopefully this is not going to become like confusing, but this statement applies to everything up until here. So this, the 1/2 inch diameter is literally just at the exit of the faucet.
So when we're talking about major losses, we're just talking about within the pipe.
Yep. Yep, and we're about to address the fittings next, but before we do that, I want to point something out to you. So you'll notice that our pressure at 0.1 that we calculated with no losses in the system was 10.7 PSI. When we have just the losses from kind of frictional losses in that piping, it goes all the way up to 20.3 PSI. What that means is in order to get the same behavior at the end faucet, you need a lot higher pressure at the start of the system to force the fluid through there because it has to overcome the frictional losses. Okay, so what you'll notice is if you have problems like this, if you neglect losses in the system, the pressure that you're required to input into it or the work you're required to input into it is going to be much lower than if you do have losses, or you can think of them as inefficiencies. So yeah, okay, let's do the fittings now, the minor losses. I'm not going to use this last page if you're using the hard copy and you want to just write over those last things. That's fine. Okay. So let's do include all losses. All right, so now we need HLM. Okay. So our minor losses are either LE over D, V squared over 2 times F, or we can use V squared over 2 times K. These are the 2 versions of calculating minor losses. And so what I like to do for problems like this is I like to just make a table. So I have my fittings, the different types of fittings in my system, and then I'm going to write down the quantity that I have and then what the K value is. It helps me stay organized. Okay. Okay. So let's go back to our drawing. So we have a whole bunch of threaded 90-degree elbows, right? 1, 2, 3, 4. 4 of them. And we also have a wide open globe valve. And we have our faucet. And I'll point out at this stage here, our faucet, they already give us our KL value, which is very kind of them. Okay, so I have three different types of fittings in here. So I have a 90-degree elbow, and it was threaded. There was 4 of those. I have a wide open globe valve. And then I also have that faucet. There's just one of these last 2 each. This K value was given to us in the schematic. These other 2 we're going to look up in our table, which I'll show you in just one moment. Okay, so I'm going to go back to our minor loss table. Here we go. So we have a standard elbow, 90 degrees, which is 30. So our LE over D is 30. And then our globe valve fully opened is 340. So 340 and 30. So this is LE over D, and this is LE over D. Yep.
Where was 2 again?
Oh, 2 was in the picture. Right there at the top.
Use F from the last one.
Yep. And then on an exam, I would very likely give you, so there's alternately for these 2, K is equal to 1.5 or K is equal to 10 for these 2 fittings. There's another table that I didn't reproduce here, but I would give it to you on an exam. So this is from table 8.4 in the book. Okay, so I'm going to use the K values just because that means my equation's the same for all 3 of our fitting types. And what I'm going to do is I'm going to say, okay, I have 4 of my elbows. So I have 4 times V1 squared over 2 times 1.5. So that's my K value for those elbows. Plus I have V1 squared over 2 times 10. This is for my globe valve. And then for my faucet, now I'm going to use V2, all right? Because V2 is coming out of the faucet. So I have V2 squared over 2 times K equals 2. So I have, this is my faucet. That's this guy. This is my globe valve. That's this guy. And then these are my elbows, which is this term here. So notice they all sum together. So I could have written the V1 squared over 2 times 1.5 4 different times, but then I just multiply by 4. Okay. All right. And so we have our equation that we have rho G Z2 plus 1/2 rho V2 squared minus V1 squared plus density times our major losses from the previous part. And now we're going to add in our minor losses. And when we do that, we get 30.5 PSI. All right, so our pressure demand has gone even higher now that we have those inefficiencies to overcome in the fittings. Yeah. Oh, it doesn't matter. You can use either one. So I can use either one of these expressions for HLM. So there's LE over D. I could use that if I wanted to use the 30 and the 340. And then I would just have to multiply by the friction factor. And then if you have K, then you can just do the V squared over 2 times K. They're equivalent. Mhm. Question? Oh, I thought I sensed one. That's okay. Any questions on the process or kind of any part of these problems? These are very useful. I've done these calculations when I redid a bathroom in my house, so.
Basically, not the same, right?
You can use it, yeah, sure. Mhm.
Would that be different for?
So you should, it's possible you could get slightly different results than the K, just because they come from 2 different tables and 2 different sources, but you should get, I would treat them as equivalent in grading, and they should give you results that are fairly close. Now we're gonna do practice exam. Okay, so this was a former exam that I wrote. This was a real one. So yeah, expect something similar to this. Okay, first question is we are given a x component of velocity for a flow and a y direction component of velocity. And we want to determine an expression for the z component of velocity for a steady, incompressible flow. All right, so for this one, we are going to use conservation of mass. So our governing equation is the following. So we have the time derivative of density plus the x derivative of density times u plus the y derivative of density times v plus the z derivative of density times w is equal to 0. Right? The next thing we're going to do is we're going to write our assumptions. Which were already given to us in the problem. So we have steady, incompressible. And then I'm going to simplify my equation using that. So since it's incompressible, density comes out of all these derivatives, and then we can divide through by it. And since it's steady, we can get rid of the time derivative as well. So our simplified equation is the following. So we have partial u partial x plus partial v partial y plus partial w partial z is equal to 0. Oh, you guys, I didn't print this out. Do you need paper? You sure? Sorry, I totally forgot. Okay. All right, so we already have u given to us and v given to us, and we want to find this one, w. All right, so I'm just going to plug in u and v, take my derivatives, and then I'm going to do the separation and integration to find w. All right, so we've got partial x of u, which is 2x squared y cubed plus xz squared plus the y derivative of the y component of velocity, which is minus 2x squared over 3y cubed plus partial w partial z is equal to 0. All right, so I'm going to do my derivatives. So I have 4xy cubed plus z squared. And then I have 2x squared over y to the fourth plus partial w partial z is equal to 0. So far, so good? Cool. All right, I am going to now separate variables and integrate. So I am going to move all of this stuff over onto the right-hand side. So I minus 4xy cubed plus z squared plus 2x squared over y to the fourth partial z. I'm being intentional with my partial derivatives, just to remind you that the constant of integration might be something other than a constant. And then I'm going to integrate both sides. So I have w is equal to minus 4xy cubed times z plus z cubed over 3 plus 2x squared over y to the fourth times z plus a function of integration that could depend on x and y. Okay. Questions on this one? Okay, if not, I will move along. Bless you. Now we have another problem, which is similar to, with a little bit of nuance to things that we've seen in class / homework. So we have an incompressible fluid flowing steadily between two plates, separated by a distance h. The left plate is moving upward at a speed of u, and the right plate, whoopsies, moves downward with a speed of u. We want to determine an expression for the velocity. So the hint is that there are two components that we need to find. And I forgot to include this. We're going to let x equals 0 be at the left plate. Okay. Okay, I think I mentioned this before, but I will force you to simplify the equations for me and write down your assumptions and whatnot, okay? So the first step of this is we want to simplify conservation of mass and Navier Stokes equations. I've also printed them for you so you don't have to write them down. I started doing this after one student like transcribed the equation wrong and then it threw everything off. And I'm like, all right, forget it. I'm printing it. So yeah. Okay, so first, these are our governing equations that are already written for us. So we want to write down our assumptions. All right, so we have incompressible, that's already given to us in the problem. We also have steady. And I'm going to also assume that it's fully developed. All right, our velocity is generally going to move in the y direction. So that means derivatives with respect to y of velocity are going to be 0. And then I'm going to make an argument that this is at most 2D. So everything's going to be a function of just x and y. This means that w is going to be equal to 0, and then derivatives of velocity with respect to z are going to be 0. And then last but not least, I'm going to say that gravity is equal to 0 minus g and 0. Yeah. So in order to simplify the Navier Stokes equations so that we can solve them, we always have to assume fully developed.
Is that always the same?
So this is just depending on my coordinate system. So since I put x and y in this, I configured x and y like this, and then I put g here. That's where that comes from. Mhm. Other questions about assumptions? Nope. Okay, cool. Alrighty, so let's simplify. For incompressible, we know we can take the density out of our derivatives and divide through by it. So I'm going to get rid of density. The momentum equations, so Navier Stokes equations, are already written assuming incompressible, so we don't have anything to do with that. For steady, I can get rid of my time derivatives. Of which there are 4. And then for fully developed, I'm going to get rid of any derivative with respect to y taken of velocity. All right, so I get rid of this guy, this one, this one, this one. And then these 3 on the right-hand side as well.
So question about that. So it's any way that the actual fluid is going, so this is going down in that direction, that's fine.
Yep. Yep, so fully developed just means that as you're like moving along with the flow, the shape of it is not changing. So if you are at this point versus this point, the profile of velocity should be the same, which means that any changes with respect to y are going to be 0.
Okay.
Yep. Okay, we're also assuming that this is 2D. So the first thing I'm going to do is I'm going to eliminate terms that have w in them. So the z component of velocity is going to be 0. So this goes away. These 3 terms on the left-hand side go away, as well as this term. And then I get rid of these terms for the z direction equation. And then I can also get rid of my z component of my z derivatives of velocity, which are these 2 in addition. Okay. All right, so let's write down our simplified equations here. So this one has become partial u partial x is equal to 0. This one has become u partial x is equal to, oh, wait, let me deal with gravity. Sorry. So I don't have a component for gravity in x or z, so I'm going to get rid of these terms too. So this is equal to minus partial p partial x plus mu second derivative of u with respect to x. Our y equation is similar. So I have u times partial v partial x is equal to minus rho g minus partial p partial y plus viscosity times the second derivative of v with respect to x. And then our z component is just that partial p partial z is equal to 0. Yes.
I've only really seen, like, when we cancel out like the Z component, I've never really seen it be used for much. Is there ever gonna be a use for it?
So there is a use for it because we've gotten rid of, like, for example, the terms that really help us to get rid of are like these ones and these ones. So if those are still in the equation, this would quickly become not solvable analytically.
So it's just to confirm.
So it's basically just to simplify. So if we kept them, then we would be solving for, we'd have to find an expression for U, V, and W. So we'd have like a coupled system of equations that would get very tricky to solve. Yep. Okay. All right, so we're in much better shape than when we started, right? These equations are a lot simpler, but they're still not quite in a position to solve. All right, so the main problem here is these terms. So these are nonlinear terms because we have a variable times a derivative of a variable, which is rather problematic for us. So what we're going to do next is we are going to solve our conservation of mass equation to figure out what U is and then simplify further. So the first thing that I want to do is I want to say, okay, U can be a function at most of X, Y, Z, and T, right? That's the full possibility for it. But we know that our flow is steady, so it's not going to depend on time. We know that it's fully developed, so it's not going to depend on Y. And we also know that it's 2D at most, so it's not going to depend on Z. So that means that U is just a function of X. And so I can turn this partial derivative into a total derivative. All right, so I have du dx is equal to 0. Which that just means if we separate variables and integrate this, U is equal to some constant, C1. All right, and we want to use boundary conditions to figure out what this constant must be. So for cases that have walls, boundary conditions are going to generally exist at the walls or at a free surface. So if we look at this point here where X is 0, so this is the component of velocity that we care about. We're going to say these walls are impermeable. Nothing can be flowing in or out of them. So that means that U must be 0. Yes.
Can you just write that it's impermeable, or do you want to see us show that it's a constant also?
So I would prefer, I mean, that kind of goes down to skipping steps. If you just wrote du dx equals 0 and then U equals 0 in parentheses impermeable, that's fine. It's technically skipping a step, but that's fine. Okay, so we have a solution for one of our components of velocity. Actually, let me give this a different color. Not used orange. Okay, so we have U is equal to 0. All right, so I am going to use U equals 0, and I'm going to simplify my momentum equations even more. So this goes away because U is 0, and this goes away because U is 0, and this goes away because U is 0. So we get rid of our left-hand terms in the X and Y direction, as well as our rightmost term from the X direction equation. All right. Okay, so we already have U equals 0, so that's one component that we've already found. The other equation that we're going to use, our X equation now just looks like our Z equation. We just have partial P partial X equals 0. So we're going to use our Y equation to solve for B. So here we have rho G plus partial P partial Y. I've just moved those terms over to the left-hand side. And I'm going to also divide by the viscosity. And this is equal to d dx dv dx. I've switched to a total derivative for the exact same reasons as I did in conservation of mass. Are we feeling okay so far? Ish, okay. Okay, so I'm just gonna separate variables and integrate this thing 2 times. So first I will move over my dx. And then I'm gonna integrate. All right, so all of this stuff in the integrand on the left-hand side is a constant with respect to x. So it hangs around and just picks up an x. And then we also have a constant of integration that I'm going to call C1. And then our right-hand side is just dv dx. Okay, I'm going to separate variables and integrate once more. So I have 1 over mu rho times g plus partial p partial y times x plus C1, all of that times dx. And then that equals the integral of dv. Okay. All right, so I have, when I integrate this x, I'm gonna pick up a 1/2, so I'll put that up here with the mu. I keep around my rho g plus partial p partial y. And I have x squared now, plus c1x, plus a second constant of integration, c2, and this is equal to v. Hopefully this is starting to feel fairly familiar. So this is generally kind of the form of what we're going to get when we do these problems. And the kind of the new bit for this question is the boundary conditions. So finding C1 and C2 is going to be a little bit different than what you've seen so far in class and homework. Okay. So the boundary conditions to find C1 and C2, we need 2 of them. So we're going to look at what's happening at the walls. All right, our no slip condition tells us that the velocity of the fluid has to be the same as the velocity of the solid surface where it's touching. So on the left wall, so at x equals 0, we know our velocity has to be positive u. And then at the right wall, it has to be negative u. All right, so I'm just going to write that down here. So we have at x equals 0, v is equal to u. And at x equals h, v is equal to negative u. Does that statement feel okay to everybody? Okay, great. So we're just gonna apply these systematically. So I'm gonna do this one first and I'm gonna do this one second. Since v is not equal to 0 on either plate, they're both kind of equally algebraically irritating, but they're not that bad. All right, so let's do this one first. So I'm gonna plug in x equals 0. So I end up with C2 is equal to capital U. So that one's fairly straightforward, not too bad. But it's not 0. All right, and then for the second one, I'm gonna plug in x equals h. So I have 1 over 2 mu rho times g plus partial p partial y. I'm plugging in h for x, so I have h squared plus c1h plus c2, which I now know is capital U. And this is going to be equal to negative u. Oh, so I just substituted, I'm substituting x equals 0. So this is 0 and this is 0. That makes sense? Okay. All right, so I am going to now solve this for, sorry, C1. All right. So I have that C1 is equal to 1 over H minus 2U minus 1 over 2 mu rho times G plus partial P partial Y quantity H squared. So I'm going to simplify this just a little bit. So I have minus 2U over H plus 1 over 2 mu rho G plus partial P partial Y H. Okay. Okay, so these are my two constants, and I am just going to put those back into my expression for V. So I'm going to do a little bit of consolidation. So I have a couple terms that have this 1 over 2 mu rho G plus partial P partial Y hanging around. So I'm going to group those together. So I have X squared, and then I have minus H times X. All right. And then I also have minus 2U over H times X plus my C2, which is U. So just to be abundantly clear, my C1 times X term is broken up into here and also here. It's okay if you don't factor things out on the exam. I mean, I would love you for it, but if you don't, that's okay. Questions on this one? Did it feel fairly like reminiscent to what we've done a number of times at this point? Okay, cool. Yeah.
Do you have one question on topic 4 where it was, I think it asked for Q, but it was a question like this and it had
Yeah.
degrees and stuff?
Yeah,
Would you have something?
I could, but I never have before. So once you have the velocity, finding Q is really simple because Q in this case would be the integral from 0 to H of V dx, and then like whatever the depth might be, B. So you would just have to integrate this equation with respect to X.
Oh.
So it's not too bad. So I wouldn't put it past me, but I never have before. But it's really not that bad of a question if I do ask you that. Okay. Okay, question 3 is a Bernoulli question. And I think I've already told you this before, but I do this on every exam, so just expect it. You'll be given situations and you need to determine which ones you can use Bernoulli for and which ones you can't, and say why. So if you remember when we talked about the Bernoulli equation, the assumptions that we made to come to that equation was we had to have a steady flow. It had to be an incompressible flow. We had to be able to follow a streamline, meaning it has to be laminar, essentially. And then those are the 3. Those are the big 3, okay? Okay, so let's consider our options. So we have an F1 vehicle driving on a road course. Oh, this is a thing that actually happened. Anyway, sorry. I was very excited about it when it actually happened in real life. So when the vehicle passes over a sewer cover, which is a manhole cover, the cover is lifted out of the hole and becomes lodged in the undercarriage. If the pressure inside the sewer is atmospheric and the cover has a mass m, determine an expression for the velocity of the car to cause the cover to be removed from the street. Okay, what do we think about that one?
That would go pretty fast.
Huh?
That would be going pretty fast.
It did have to be going pretty fast. But for this one, we're gonna say it's okay. You could probably make an argument that the F1 car goes fast enough that you might have to take into account compressibility, and I didn't give you a velocity to really check. So I would be okay with if you came up and asked, can I assume incompressibility? And I would tell you yes. Okay. The second one is water falls chaotically over a distance h at Niagara Falls. Given that the water reservoir it draws from is large enough such that the water at the surface can be assumed to have zero velocity and atmospheric pressure, if you are able to measure the velocity of the water at the bottom of the fall as v, what is the pressure at this point? What do we think? No, why? Yeah, so this is turbulent. So we cannot do that. Okay, third choice is you are designing the fuselage for a rocket car that will hopefully beat the current land speed record, which breaks the sound barrier. Determine the pressure at the nose of the vehicle given the vehicle's maximum velocity v. So this one, we're going fast enough that we're breaking the sound barrier, which means the velocity is above Mach 1. So this is definitely compressible. Okay, so this is compressible. Okay. The next part is solve the problem that allows the use of the Bernoulli equation. Okay. And if you pick the wrong one, but you generally apply the Bernoulli equation correctly, if it could have been used, that's fine. I won't like double take the points. Okay. Okay. So we're going to look at the first option. And so we want to find an expression for the velocity of the car. All right. So we have a race car, a very simple race car going at a speed v. And we have this manhole cover here. And the manhole cover has a mass m. And we're going to assume that this is our streamline from point 1 to 2, where we have, this is P1 is P atmosphere. And then P2 is not going to be atmospheric pressure because it's going to be moving with the speed of the car. Roughly, okay? Okay, so if we want to know the conditions for the cover to lift, what we need is a free body diagram on the manhole cover. So I'm going to do a free body diagram. So we have the weight of the plate is mg. And then we have P2 times the area of the manhole cover pushing down on the top. And then atmospheric is underneath the manhole cover is what it said in the problem. So we have atmospheric pressure times the area of the manhole cover pushing up on the bottom side. Right? So this is going to lift when the pressure on the bottom overcomes the pressure on the top and the weight. So when P atmosphere times A is greater than P2 times A plus mg. That makes sense? Okie dokie. So we need to use Bernoulli to connect P2 with the velocity of the car. All right, so Bernoulli from 1 to 2 gives us that P1 over rho plus V1 squared over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. That's just Bernoulli equation. I'm assuming that point 1 is super far away from the car, so this is 0 velocity, and then P1 is P atmosphere. All right, and then I'm also going to assume that Z1 and Z2 are the same, so I can get rid of these two. Z1 equals Z2.
Why is we want to?
So we're assuming that we're picking a point like really far away from where the car is and the air is just stationary. Okay, so that means that we have P atmosphere over rho minus V2, which V2 is just V, right? That's just the velocity of the car squared over 2 is equal to P2 over rho. And then I'm going to multiply through by rho so I can have an expression for P2. Okay, so I'm going to take this expression and then I'm going to just put it into here. So I have my atmospheric pressure times A has to be greater than P2, which is P atmosphere minus rho V squared over 2. That quantity times A plus mg. I have P atmosphere times A on both sides of this equation, so I can just subtract P atmosphere A from both sides. So this cancels with this. And then I'm going to move my rho V squared over 2A to the left-hand side. So I have rho V squared over 2 times A is greater than or equal to M times G. All right, and now I'm just going to solve for V. So I have V squared has to be greater than mg times 2 divided by rho A. And then I'm going to take the square root of both sides. Okay. This did actually happen, by the way. There was like a formula race on like a city street course where there are manhole covers. Crazy. He must have been cooking. Because those things are heavy. I don't know if you, yeah, they're pretty heavy. Okay.
Question
Yeah,
about
what's up?
we actually finding, some of the,
Yeah.
um, we gave it away with the first one.
So you could, the first one was maybe a little ambiguous, you know, because you could maybe reasonably make an argument that it might be compressible. So I would suggest like read all of them. And I won't give you a circumstance where like multiple of them could use Bernoulli. So like, I think the second two or the last two are kind of obvious that you can't. So by process of elimination, you could also be like, okay, you know, it's gotta be the first one. You could also ask me questions like, be like, can I assume this is incompressible?
Okay.
Okay,
For the free body diaphragm, how did you get, E2A?
so P2 is our pressure on the top side of our manhole cover. The force due to pressure is pressure times the area that it acts over. Right? And then I have drawn them because I've drawn them in the way I have because pressure is always compressive, so it's always going to act onto the body. So that's why the top one points down and the bottom one points up. Does that help? Okay, great. Other questions? No? Okay. This one used to be different. I used to have the pipe like became smaller and there was like a contraction in here. I simplified it because it was long. So, yes. Okay, so this is essentially another example of kind of what we just did in the beginning of class. And I really like this question. I wrote it myself. Well, I wrote all these myself, but this one's about geothermal heat pumps. So this is a kind of a sustainable way of heating or cooling your house, which is very cool. I aspire to have one of these in my house one day. We'll see. But anyway, okay, so in these systems, groundwater is used as an exchange medium for the HVAC system rather than the outside air. So in this case that I'm showing you here, the house is next to a pond, so it's going to use the pond water to do this. So we're going to consider this geothermal pumping system. We're going to assume the fluid pumping through this is water. So I've given you the density and the dynamic viscosity. Note, I'm also using SI units. And the system has a volume flow rate of 9 liters per second. And I've given you the conversion from liters to cubic meters. The pipe is made of PVC. I've also provided you already with the relative roughness, so you don't need a table for that. And we want to determine the work required to be input by the pump if the pressure at the pump discharge point is 200 kPa. And we want to make sure we've considered all losses in our system, okay? So I can't remember which of you asked about, the W dot terms. This one is pretty explicit because we're trying to find it. So we want to determine the work. And we've drawn in here, this is the pump. Okay? All right, so if we just look at this drawing for a quick minute, we have two 90-degree elbows in here. We have a pump, and then we have an entrance. So we're gonna have to take into account this entrance from the pond into our piping system. And then otherwise, we just have two lengths of pipe at the same diameter, okay? So let's write down our governing equation first. Okay, so we have P1 over rho G plus alpha 1 V1 squared over 2G plus Z1 minus P2 over rho G plus alpha 2 V2 squared over 2G plus Z2 minus W dot over M dot G is equal to the major losses plus the minor losses. All right, so we want to find this. Okay. And we are given a lot of information in here. So we are given that the pressure at point 2 is 200 kPa. right? And we need to say something about Z. Where do we want to place our Z equals 0? Point. Yeah, it doesn't really matter. I am going to put it like right here. So this is Z equals 0. All right, so I'm going to say Z1 is 0. Oh man, I think I simplified this problem too much. Blast. Well, you just saw it in the example earlier. So since the diameter is the same all the way through the system and from point 1 and to point 2, our V1 squared and V2 squared are going to be the same. So they just cancel each other, which is a little disappointing. On an exam question, you're almost guaranteed to have to calculate the Reynolds number and find alpha. But I aggressively simplified this. So V1 equals V2 because D1 equals D2. So they just cancel each other. Okay. All right. What is Z2? Yeah, so we have that. So this is 6 meters. What about pressure at 1? We're given what depth it's at in the pond.
Or is it 5?
Yep. So pressure is going to increase with depth, so we'll keep it a positive 5. Very good. Thank you. So P1 is equal to P atmosphere plus rho G H, where this is 5 meters. Excellent. And then I would like to just quickly kind of make a few notes about minor and major losses. So major losses, what do we got? All of the piping is the same diameter. So how much length do we have? We have 31, we have a 25 meter section and then a 6 meter section. So we have 31 meters of D equals 100 millimeter pipe. All right, so we'll have that to contend with. And then for our minor losses, we have the entrance from the pond. So this is 1. Let me call it A. So we have A. We have 2 elbows. And that's all. Nope. Nope, you don't have enough information to figure that out. So we are not going to, the problem has not given you any efficiency information for the pump, so you can ignore that. That's a fair question though.
The problem we did in class, I know you said B1 equals B2 because B1 equals B2.
Yeah,
So 2 is not like a different value. We don't specify that.
right, I would have to tell you. So like in the problem we did in class, it said the faucet has a different diameter at the outlet, so that's how we knew.
If it doesn't say.
If it doesn't say, you can assume that it stays the same. Yep. You can also ask me that if it's not clear. Yep. Okay, so this is the approach. All right, so I'm gonna write a simplified version of this. So we have P atmosphere plus rho GH divided by rho G minus P2 over rho G plus Z2 minus W dot over M dot G is equal to HL plus HLM. Actually, maybe this wasn't too bad. We still need to calculate like the velocities and Reynolds number to do the major losses. This wasn't too bad. I take it back. Okay, so let's do our major losses first. So our equation for our major losses is that we have HL is equal to L V squared over 2 times D times the friction factor. Right? So we don't have V yet and we don't have F yet. So let's find V first because we're going to need V for the Reynolds number anyways. So V is equal to Q divided by A. And we were given Q and we can figure out A. So Q, where are you? 9 liters per second. So that's 9 times 10 to the minus 3 meters cubed per second. And then we're going to divide by the area. It's circular. So we have pi over 4 times the diameter, which is 0.1 meter squared. And we get 1.15 meters per second. Okay, so let's use that to calculate the Reynolds number. So we have rho times V times D over mu. So we have, this was given, rho was given to us, it's 1,000. Then we have 1.15 meters per second. Diameter is 0.1. And then we're dividing by 8.9 times 10 to the minus 4. And this gives us 1.29 times 10 to the 5th. So what do we think? Laminar or turbulent? So this is a lot bigger than 2,300, right? So this is turbulent. So we're going to use alpha 1. Well, we don't care about alpha 1, I forgot. We just need the Reynolds number. All right, we also need our relative roughness. So epsilon over D, they gave us epsilon, I gave you epsilon in the problem statement, so it's 0.015 millimeters. And then diameter in millimeters is 100, which means epsilon over D is 1.5 times 10 to the minus 4. All right, so let's find, so we have V now, so that's good. We know L already because we have 31 meters of pipe. So that's L. And then we know D, that's given to us in the problem. So we need to figure out F. So we're going to use the Moody chart. First, let's see if I have. No. I thought it was the last thing I copied. You get a giant Moody chart for the equation sheet. Okay. Okay, excellent. Stay. Okay, so we have a relative roughness of 1.5 times 10 to the minus 4, which is 0.0000000015. So 1.5 times 10 to the minus 4 looks like this. So we are going to be between this one and this one, right? So this is going to be our relative roughness, and we're going to generally have a curve that goes sketched in like this. Okay. All right, our Reynolds number is, so this is epsilon over D. Our Reynolds number is, I'm going to call this 1.3 times 10 to the 5 because that just makes it a little easier. All right, so we have 1 times 10 to the 5 is here. And 2 times 10 to the 5 is here. So I'm going to be partway through this line here. So we're looking at roughly at this spot here. So I'm going to take this intersection point and move it over to here. All right, so we find that our friction factor is roughly 0.017. As long as you show your work and are roughly reasonable about this, I'm flexible. Like if you said 0.018 or something, that's fine. Okay. All right, great. So this means that HL is equal to L V squared over 2D times F. So we've got 31, is that right? 31 meters? Yeah. We have 31 meters times 1.15 meters per second squared divided by 2 times 0.1 meters is our diameter times 0.017. And I did not actually calculate that all out, but that is a number. Okay, so those are our major losses. And recall that if we want lowercase HL, that's just capital HL divided by G. Okay. So we got that. Let's do minor losses now. So we have an entry at 0.1. We have 2 elbows. And then we have, that's all, right? Yes. Okay, so let's find our K values for those. And I'm going to take us to the equation sheet. Okay. Oh, and I can't remember what the elbows were. So these are 90-degree regular threaded elbows. All right, so we've got 90-degree elbows. We want to do regular threaded, which is here. So K is 1.5. So I'm going to put that in here. So our K value is 1.5. And now we want to look at our entrance. So this is the type where it's not chamfered, it's kind of sticking into the large body of water. So we are going to look at this reentrant type like this. And we're going to assume a worst case scenario and we're going to use 1. Okay. So we're going to do K is equal to 1. So our HLM is V squared over 2 times K. So in this case, we have V squared over 2 times 1 plus 2, because we have 2 elbows, V squared over 2 times 1.5. Okey doke. And then also recall here that HLM is H, capital HLM divided by G. All right, so now we're just gonna put it all back together. So we have P atmosphere plus rho GH divided by rho G minus sorry, I already forgot. P2 over rho G plus Z2 minus W dot over M dot G is equal to HL plus HLM. I didn't write down the final numbers, but we have these losses already calculated. We know Z2, P2 is given. We know H, and we know obviously P atmosphere, density, and gravity. So we have everything to just solve this for W dot. Oh, and I should note, M dot is equal to rho times Q. So we have M dot as well. All right, so we just solve for W and we get HL plus HLM plus P2 over rho G plus Z2 minus P atmosphere plus rho GH rho G. Okay, looking at this, kind of where the contributions to like what work we need to put into the pump, all the pressure that's at 1, so the pressure work at 1 has a negative sign because that's kind of helping our pump. So it doesn't need to do that work to draw water through the system, but it needs to overcome the minor and the major losses. And then it also needs to make up any difference in the pressure that we want to have at the outlet. So at 0.2 compared to 0.1. Okay. Thoughts? Questions? Concerns?
We just keep the HL like that rather than plugging anything in.
Oh, I can here. Let me. So we already have these capital H's. So you would just plug in all these numbers. I forgot to do it in my notes, but that's just calculator work. Yeah.
Are you gonna give us the, like, for example, you did 90-degree regular pivot elbows? You're gonna.
I would give you that sort of information, and then this is the equation sheet that you'll have too. It'll have all these tables in it. And then one thing that's not in this problem statement that I would add, is like for the reentrant one, it has 0.5 to 1, so I'd probably say like assume higher K values, you know, if there's a range. Mhm.
And then if you have contraction or expansion, that's when you would need to do,
This chart.
wouldn't you also have to do, you would have to find. You have to find something twice.
I don't think there's anything you need to find twice. If you,
Sorry, was that one question where it's like D1?
uh-huh.
And then do you remember how like someone asked you would have to find something twice?
Oh, that is for the major losses. So if you had two different pipe sizes, like for example, the original version of this problem had, like, this was a smaller pipe here. I did not draw that well, but there was an expansion that happened there and it went to a small pipe. So if that were to happen, then you would need to calculate the major losses for the small pipe and for the large pipe
And then you would have to use the contraction and expansion.
for the minor losses. Yep, yep. Other questions?
If you want this creates, is that constant? Constant equation in the brain?
Wait, what?
That.
Oh, here?
Yeah.
So that is just the hydrostatic equation for here. So this, let me write that down.
Is there a possibility that we could be clear that people for the whole pump rather than having more than W over MQ? It's an H. Oh,
The W dot?
yeah, well, the W dot over M dot G. Doesn't equal H as well.
Oh, yeah, so W dot divided by M dot G would be, the unit would be meters. Is that your question?
Well, I'm saying if we could just do that outright.
Yeah, so if I gave you that in the problem, it would look something like the pump can produce a head of 10 meters, for example. And then in parentheses, I'd probably write like W dot divided by M dot G is equal to 10. Yeah. But that's how it's usually like, if someone were to just say that to you, like the pump can deliver a head of 10 meters, that's what they're referring to. Yeah. Other questions? How did these questions seem? Okay-ish? Okay, cool. All right, so this is the start of the heat transfer unit, which will not be on the next exam, but please still pay attention. And this topic is pretty short. And it should essentially be a review of 2500, hopefully. So if that feels like distant memory, then pay extra attention now.
So we're gonna be using tables?
Huh?
Are we gonna be using tables?
I mean, we're not gonna be doing any, are we gonna? I'm trying to remember. So there could be some interpolation light, like it's not, we're not gonna be using like the steam tables.
Okay.
Yeah. You don't like the steam tables?
When they work, it's fine, and then like occasionally, it depends on the problem. Sometimes something goes wrong, and it just takes me forever to figure out.
I don't think you will have trouble with this, hopefully. Okay, so now that we're switching to heat transfer, I want to just define kind of some terms that we're gonna be using a lot, and I apologize for some of this because we're gonna be using U's and Q's, but for entirely different things now. This is kind of the hazard of combining two topics into the same class. So we'll just do our best, okay? Okay, so the first one is capital U. This is thermal energy. It's gonna have units of joules, and this is energy related to the molecular structure or the molecular activity of a system. This is a form of internal energy, and it's associated with temperature. It's really raining now. Temperature, of course, is called T. It has units of Kelvin or Celsius or Fahrenheit, I guess. And this is an indirect measure of thermal energy stored in a system. Now, instead of being flow rate, Q is going to be heat transfer. So this has units of joules. And this is the transfer of thermal energy due to a temperature gradient. Meaning a spatial difference in temperature. Spatial difference. All right, so this is the idea that temperature is always going to flow from a higher one to a lower one until equilibrium is satisfied or achieved. Q dot is the rate of heat transfer. So this is the rate of heat transfer from one system or region to another. The dot just indicates a time derivative. So this is dq dt. And then the units are, of course, joules per second, which is watts. Heat flux is going to be Q dot, but divided by a surface area. So it gets a little q because it's like a specific rate of heat transfer. So this is Q dot divided by area. So this is area. So rate of heat transfer per area, per surface area. Thermal resistance is R, that has units of meter squared Kelvin per watt. This is a material property that describes the tendency to resist heat transfer. And it's the opposite of thermal conductance, which has also the variable U assigned to it, which is great. I love that for us. And this is also a material property that describes the tendency to conduct thermal energy. And then last but not least, we have thermal conductivity, which is different than conductance. We're going to use this one actually quite a lot. So the thermal conductance isn't really going to come up so much. So the multiple U's is really not an issue. We're going to use thermal conductivity K. That has units of watts per meter Kelvin. This is also a material property. that describes the tendency of the material to conduct thermal energy. But the key difference here is that this is per thickness of the material. All right, so it matters how much of it you have. Okay. There are three mechanisms of heat transfer. First one is conduction. We also have convection and radiation, right? So for conduction, this is heat transfer within a solid or also a stationary fluid. All right, this is caused by the random motion of atoms, molecules, and electrons. And energy always transfers from more energetic particles or higher temperature to lower energetic particles or lower temperature that are adjacent. So energy transfers from more energetic particles. So this means a higher temperature to lower or less energetic particles, which means lower temperature, that are adjacent. All right, this means that direct contact is required. This is all old hat at this point, right? Okay, cool. Okay, so conduction is governed by Fourier's law of conduction. So we have that Q dot is equal to the negative conductivity of the material times the gradient of the temperature. All right, so, and I'm gonna call this, I'm gonna put a subscript on these so that we know kind of what mechanism the Q dot is referring to. So this is conduction. So we have minus K gradient of T. So this first term here is heat flux. This is the conductivity. And then this is the temperature gradient. All right, the negative sign may seem a bit curious, but essentially it arises because heat is gonna flow from hot to cold. So we need that negative sign to account for that. So if this is X and then this is temperature, and we have temperature at 1 higher than temperature at 2, which direction is Q dot going to point? So Q dot is generally going to go like this, right? So our heat transfer is going to go from left to right, but you'll notice that this slope is negative. All right, so that means that the gradient of T is negative. But we know that Q dot is positive, so we have that minus sign out front to account for that, okay? Okay. So we want to consider, just for as an example, the case of 1D steady conduction across a plane wall with constant K. All right, so I'm gonna approach this just like how we did in the fluids kind of portion of the class. All right, so I'm gonna rewrite out this gradient. So I have partial t partial x I hat plus partial t partial y j hat plus partial t partial z k hat. That's just my gradient. All right, and so if this is one dimensional, I'm going to assume that one dimension is x. So all of my derivatives with respect to y and z are 0. Okay, and then I'm also going to assume that this is my wall. I have a location 1 and a location 2. And the distance between them is L. I'm also going to assume that T1 is greater than T2. So when I look at this simplified equation, I have Q dot for conduction is minus K dt dx I hat. And I can calculate this gradient. I can do this slope with the information that I'm given. So I have T2 minus T1 divided by X2 minus X1. So that's just the slope. All right. And so this gives us minus K delta T over L. And so this is referred to as the temperature drop. I'm going to do the circuit analogy just real quick. So our equivalent circuit analogy is the following. So we have our first temperature, our second temperature, and then we're thinking of our material between these two temperature readings as a resistor. So this is R. And then on here we have Q dot of convection. So from Ohm's law, we have that the change in voltage is equal to the current times the resistance, which in analogy to the heat transfer, this is our change in temperature is equal to Q dot times R, where R is L over K. Okay. I'm not going to use the circuit analogy that much. So there it is. Okay, so just a little thought experiment before we wrap it up for the day. Given this definition for Q dot for conduction, so we have minus K delta T over L. How might you reduce Q dot due to conduction? Any ideas? If you wanted to make Q dot smaller? More similar? Yeah. So delta T gets smaller, right? What else? There's something in the denominator.
Wouldn't K get big? No, smaller.
Yep, smaller K. So choose a material with smaller K. Okay, there's one more thing. What should we do with L? Yeah, increase L. Okay. Okay, I think we can probably stop here. I feel that if I keep going, your brains will melt. So let's just stop here.